All right, welcome everybody. Today we're going to talk about the third day of graphing polynomials. And after the previous two lessons, you now have all the skills you need to go ahead and graph from scratch. We're going to strongly suggest that you try to do all these problems without the use of a graphing utility. While it is okay to use Desmos or your graphing calculator to check, the better equipped you are to have these skills to do it by hand is going to help you not only as the year progresses, but certainly next year when you might not have access to a graphing utility. So take a look here at number one. Notice that while I don't actually give you a coordinate plane, you're just being asked to find a sketch. So you're going to go ahead and just draw it freehand. The further you get in your mathematical career to pre-calculus and calculus, the better and more precise your graphs will get. But for now, we're just looking for a rough sketch. Here in number one, I want to point out to you that you actually have the problem both in standard form, which means it's been multiplied out here in green, and then you also have factored form, which is here in orange. In order to find the zeros, you have to have factored form. So you're going to go ahead and list each of your x's and then denote any multiplicity. So x plus 4 gives you -4, -1, and then +3. Those are all multiplicity ones, which remember you can write or not write. It's implied if you don't say anything. Remember that at a multiplicity one, the graph is going to cross the x-axis at each of those locations. For the remaining three questions, it's actually easier to use the green standard form because of the fact that you have a nice multiplied out positive x to the third. So 3 is the degree, which is clearly odd. The sign of the leading coefficient is positive. Whether you've memorized it at this point or you still have to look it up, the end behavior is down up. So you're going to go ahead and draw yourself a little graph here. You're going to go ahead and denote all of the x-intercepts. So 3, -1, and -4. Because of the fact that the end behavior is down up, that means that you are going to start facing down and you are going to end facing up. Then for each of those x-intercepts, you're going to go ahead and cross because of the fact that it's a multiplicity 1. So because it's a multiplicity 1, you're going to go ahead and cross at -4, go up a little bit. Then you're going to turn back down and cross through -1, go down a little bit, and then ultimately cross back up to connect and make a nice smooth curve. Again, as far as how high up do you go or how low down do you go, those are things we could find either with more advanced algebra or with pre-calculus. But for today, we're just going to go ahead and do a sketch. Something else that you can find to help you, just to be 100% sure that you are in fact doing this correctly, is the y-intercept. Remember that the y-intercept is whatever you get when you plug a 0 in for all the x's. And if you're in standard form, it's just the constant. So that means that this y-intercept should be -12. Now, obviously, you're not entirely to scale here, but the fact that it's -12 certainly is reasonable in the context of the rest of the problem. So that's it. That's all we're looking for. Nice and simple. Just make sure that you have a nice, smooth, continuous curve. Let's go ahead and take a look over here at number two. Again, here in number two, you have both standard form on the left and then factored form on the right. We're going to always need factored form in order to have our zeros. So from left to right, looks like +2, -2, +1, and -1. And those are all multiplicity ones. Remember to answer the three remaining questions. If you look at standard form, that is a positive x to the fourth. 4 is even, positive. And again, whether you've memorized it or have to look it up, it's up, up. Something else you want to notice here, notice how the x-intercepts on the left side, -1 and -2, are exactly equal to the x-intercepts on the right side, +1 and +2. That just means that your graph should be symmetric over the y-axis because of the fact that your x-intercepts are symmetric over the y-axis. So that just helps you to know that you should draw your graph so that the two humps are even. So there are my x-intercepts, 1, 2, -1, and -2. Again, I'm going to start with up and end with up. Each of these are multiplicity 1, which means you're going to be crossing. So cross through the -2, go down a little bit, then back through the -1, go up a little bit, then back down through the -1, and back up through the 2. Again, because of the fact that you have x-intercepts that are equally spaced on the left and right side, that's how you know that your graph should really be symmetric. Those two humps should kind of be even as far as how low down they go. Again, something else you can point out here, the y-intercept would be +4. So +4 would be right here, which again, you can feel free to add to your graph or certainly just use as a check. Let's take a look here at number 3. So in number 3, notice that this is factored form only. So because it's factored form only, we have a little bit of extra work to do. When it comes to the zeros, if we set each of these parentheses equal to 0, we're going to get -3 with a multiplicity of 2, and then +3 with a multiplicity of 1. In order to find the degree, you would have to add up all the x's, including the squared. So this is to the first, whoops, and this is to the squared. So if you went ahead and added those up, you would get a total of 3, which is odd. Then the sign of the leading coefficient, you would have to look out front. Because of the fact that there's nothing there, that implies that it's a positive. Odd positive is down up. Draw yourself a little sketch here. So +3, -3. And again, if you wanted to find the y-intercept, you would have to put a 0 in for all the x's, which would give you 0 plus 3 squared times 0 minus 3. That would give you a +9 times a -3, which would be a -27. So we know that it's somewhere in the negative region, which again is just a quick way for you to be able to see if you're right. So end behavior is down up. And notice that at the M2, which is at -3, you have to have a bounce there. So as I come from the down, I'm actually going to touch the -3 and then bounce back down. I would actually go to the y-intercept and then turn back up, and then finish by connecting the graph by crossing at the multiplicity 1. So the y-intercept is a great way for you to double check. I mean, you should be able to find a y-intercept easily. So feel free to find it just to help you make sure that you're doing things correctly. But the truth is you should know how to do that already. Let's take a look at number 4 here. So number 4, we're back to having both versions. So over here on the left, you have standard form and then factored form on the right. So for the zeros, look at the orange. This negative, remember, it tells us about the end behavior, but we're just going to look at the x. If you were to set this equal to 0, that single x would give you a 0, and that's an M1, and then a +3, M2. In order to answer the other 3 questions, if you now look at the left-hand side, that's degree 3, which is odd. And then the sign of the leading coefficient is negative. So that end behavior would be up, down. Go ahead and draw yourself a little sketch here. So at 0 and then at +3. And again, at +3, you are going to have a bounce. So if the end behavior is up, down, you're going to start at the 0 up and you're going to end at the 3 down. You can see that the y-intercept has to be 0, 0. So go through the M1 at 0, then turn back up. At 3, you're going to touch, but then bounce back down, and your graph should look like such. The truth is, after all the prep work we've done the last couple days, you should be able to do this entire problem in probably about 1 minute. It should be getting a lot easier as you go, and dare I say, even a little bit fun. So here in number 5, again, this is factored form only, so keep that in mind. When it comes to the zeros, this lonely x here gives you a 0, M1, followed by a +2, M2, followed by a -5, M2. In order to find the degree, you would have to add up all the x's, so including their multiplicity. So 2 plus 2 plus 1, that's a total of 5. So 5, of course, would be odd. The sign of the leading coefficient out here, that would be negative. Odd negative is, again, up, down. So here I have 0, which, again, if you go through 0, that has to be the y-intercept. And then -5. I'm going to just continue to highlight where anything special is happening. So here at 2 and here at -5, you're going to have a bounce at both places. So starting up and ending down, as you start up and you head towards the -5, you are going to touch it, but then you're going to bounce back up. You're going to go up a reasonable amount. Remember, there's no right or wrong answer for now. You're just sketching it. Then you're going to cross through the 0, turn back up at the 2, bounce back down, and your graph should look like such. As long as you have a nice smooth curve, that is really ultimately what we're looking for. So one more should do it for us. And again, notice that we are only in factored form here. So remember, all the rules about factored form have to be applied. So when it comes to the zeros, that x minus 1 is going to give me a 1m1, followed by a 2m3, followed by a negative 4m2. Because this is in factored form, in order to find the degree, you have to add up all the x's. So that would be 1 plus 3 plus 2. That's a total of 6, which is even. The sign of the leading coefficient is negative, so this end behavior is going to be down, down. This is the first time today that you have graphed yourself a multiplicity 3. So I'm going to make sure that you understand how to do that. And my advice would be to over-exaggerate. Remember that at an M3, which is going to happen at 2, you have to have a flatten and then crossing. So as long as you clearly make it look different than the M1, that's really what we're going for here. And then, of course, at the negative 4, you're also going to have a bounce. So your end behavior should be down, down. And then you have each of the behaviors, so just make sure you're doing them in the right spot. Starting with the negative 4, that's where your bounce is. So you're going to touch and then bounce back down. As you head towards positive 1, you're going to cross there, go up a little bit. And then as you come back down, you have to make sure that your graph looks like a multiplicity 3. So my advice would be over-exaggerate the flattening and then crossing. I can kind of show you that again, just to make sure. So again, this is at positive 2. I know that there has to be a M3 there. So coming from the top, I know there's a point. So I'm going to get close to it. I'm going to flatten, and then I'm going to cross. So it might not, if you over exaggerate it, that's really more than enough for us. And again, as long as you clearly make it look different than the M1, which is here in yellow, which is just a simple, or let me color code that for you. Orange, as long as you clearly have a difference between what your M1 is doing, which is just a cross, and what your M3 is doing, which is a flattening cross, that's really what we're looking for. So you have seen all the combinations, all 4 types of end behavior. You've seen all the different forms, factored and standard, and you've seen all the multiplicity, which means you are now ready to create graphs on the homework from scratch. Couple other things, though, that we want to go over. So we're going back now to finding the equation of the graph in factored form, but there's a little bit of a new thing we're going to add. Here, we are actually going to solve for A. If you remember a few days ago when you did the lesson 1, you just put an A out front to remind yourself that it could be anything, but now we're actually going to find it. So you're going to start with the same 4 steps that you did the other day, and now we're going to just add one additional. So from here, the end behavior, the graph is starting down and ending up, so that is down, up. The only way that you can have end behavior of down, up is if you are odd and positive, so the sign of the leading coefficient has to be positive. So you could start by saying y equals positive a, or again, just a. For the roots and their multiplicity, you're going to go ahead and go from left to right, denoting any special cases. So here at negative 6, the graph crosses, and also here at positive 2 and positive 5. Because the graph is crossing at each of those places, those are all multiplicity 1s. The factored form of the equation, so y equals a, negative 6 becomes x plus 6, x minus 2, and x minus 5. Now, as of the previous lesson, that's as far as you would have gone, but now we're actually going to solve for a. Turns out to solve for a, all you need is one additional point on the graph. If at all possible, you should choose the y-intercept because that is the easiest one. So hopefully you notice that the y-intercept is here at the point 0, 30. If you actually now want to solve for a, you're going to take the point 0, 30. Everywhere in the equation, there's an x, you're going to put a 0. Anywhere there's a y, you're going to put a 30, and that's going to allow you to actually solve for a. We already know that we should have a positive number out front there, so keep that in mind as you proceed. So from here, I'm going to go ahead and put a 30 in for y. I'm going to leave the a, and then everywhere there is a x, I'm going to put a 0. Keep in mind, if there were any squares or cubes or anything, I would have to apply those as well. So 30 on the left, and then on the right, you're going to get 6 times -2 times -5. 6 times -2 is -12. -12 times -5 is +60. So that is 60a, which means to get the a by itself, you have to divide by 60, which means that a is equal to 30 over 60, which reduces to be 1/2. That means that not only is there a positive in front of this equation, but there actually needs to be a 1/2. So I'm out of room, but you should, in your next step, go back. Instead of having an a out there, you should now put in positive 1/2, and then this would be your entire answer. So again, we might ask you to do either. We might say just put a positive a or a negative a out front, and that will be enough. Or we might say you actually have to solve for it. And if we do say you have to solve for it, then please make sure you're able to. So there should be a 1/2 out there in order for the graph to look the way that it does. Let's see another one like that. So over here on number 8, again, starting with the end behavior, down, down. That only happens if you are even and negative. So the sign of the leading coefficient has to be negative. So if you want, you can start with y equals -a. Their roots and their multiplicity from left to right. So it looks like, again, these are all multiplicity ones. So -4, -2, 1, and 3. These are all M1s. They're not always going to be M1s. I just don't happen to have an infinite supply of graphs. So the -4 becomes x plus 4, x plus 2, x minus 1, and x minus 3. Again, while the y-intercept is always the best possible choice that you can pick. Also, just as a note, you cannot use the y-intercept if it's 0, 0. That won't work. Everything will cancel. So if the y-intercept had been 0, 0, you would have had to pick some other point on the graph, but we're most likely to give you ones where the y-intercept is going to be your best bet, and 0, -3 makes that perfectly reasonable. So I'm going to put a -3 in for the y. Then everywhere there is an x, I'm going to go ahead and put a 0. On the right, that's going to give me 4 times 2 times -1 times -3. If you go ahead and multiply that out, you're going to go ahead and get 8 times a -1 is a -8 times a -3 is a 24. So -3 equals -24a. If you then go ahead and divide by -24, you're going to get that a equals -3 over -24. The negatives cancel, and you can divide both by 3, which means you're going to get a 1/8. Now, just something to point out here, because of the fact that you already put the negative in, that's why the a that you solved for wound up being positive. If you did not put that negative out front, you would have just gotten that a equals -1/8. So it doesn't matter whether you do it in one step or 2 steps, but for your final answer here, you should go ahead and replace it. So -1/8 should be the leading coefficient that is outside. These generally wind up being some kind of a fraction, just because we don't like to be able to just guess. So if that happens, don't be worried at all. The fact that it's negative, though, that should make sense because the end behavior is, of course, down, down. So to finish up our discussion about graphs, we want to talk about the cases where everything doesn't work out so nicely. If you were to go back and review the previous 6 problems, all the x-intercepts turned out to be nice integers, +1, 2, 3, -4, 5, 6. Will that always happen? No. Are we going to try to keep it as simple as possible for now? Sure, but please keep in mind you could easily have x-intercepts of 1/2 or -3/4 or any reasonable decimals. You can also get answers that are somewhat unreasonable decimals. So let's just go ahead and kind of talk about some of these special cases. So if we do ever come across them, we won't be totally surprised. As a reminder, we've already talked about the irrational conjugates theorem, which says that square roots have to come in pairs if they're going to be x-intercepts. So if you know that the square root of b is an answer, then you know that the negative square root of b has to be an answer. if you know that A plus radical B is a solution, then you know that A minus radical B is a solution. And remember, most of the time, you write them as plus or minus. Consider, for example, this graph over here on the right. So, of course, it looks like a cubic. So because it's a cubic, we know that it has to have 3 total zeros or 3 total roots. We know for sure that there is one rational zero here at x equals 1. It's a multiplicity 1, so it crosses through, and 1 is a nice integer. Let's say we were to actually have the equation and solve this problem. The other 2 roots would turn out to be 1 plus radical 3 and 1 minus radical 3. Now, even though those are clearly not as nice as the answers that we've seen so far, I do want you to understand that they would be graphable as long as you were to convert them to a decimal. So in your calculator, if you were to do 1 plus the square root of 3, you would get a value of 2.7. If you were to do 1 minus the square root of 3, you would get negative 0.7. And if you look at your graph, that should make sense. Here, you're between 2 and 3, but a little closer to 3. And here, you're between 0 and -1, but a little closer to -1. Again, those would both be M1s because the graph is crossing there. But please make sure that you know that even though we've been nice to you and given you mostly integer answers, you could have decimal answers. So it's not totally unexpected that you would see them at some point. All the other rules for end behavior and y-intercepts and sign the leading coefficient, that would all stay the same. Then, even further, remind ourselves here of the complex conjugates theorem, which says that imaginaries also have to come in pairs. So if you had positive BI, you would also have to have negative BI. If you had A plus BI, you'd have to have A minus BI. And again, most of the time, those are written as plus or minus. Take a look again at the shape at the right here. Because it's a quartic, it has 4 total roots. We can clearly see that there is one at -2 and there is one at +2. But if you take a look at the x-axis otherwise, there does not appear to be anywhere else that the graph is crossing. So how is that possible? We know that there has to be 4 total solutions, but we can only see 2 of them. That's because those are the 2 real zeros, which means they're graphable. And then there are also 2 imaginary zeros, which we could solve for. We did that in the last section, but we can't actually graph those. So even if you can't see the imaginary solutions, you do have to be aware sometimes that they are there. So what would a question like that look like? We'll take a look at 9 and 10. Determine the number of imaginary zeros for the function given the degree and given the graph. So notice here in number 9, I am telling you that the degree of this polynomial has to be 4. That means that there has to be a total of 4 zeros, or 4 roots, 4 x-intercepts, 4 solutions. You're going to look at the graph and you're going to identify any of the real ones. You're going to count any of the crossings as an M1, and you're going to count any of the other behaviors accordingly. So you appear to have 4 crossings, which means those are all M1s. So there's a total of 4 solutions. You can see all 4 of them, which means all 4 of them are real, which means how many are imaginary? None of them, 0. If there have to be 4 altogether and 4 of them are real, it means that none of them are left to be imaginary. Compare that to number 10. So in number 10, I am telling you that it has a degree of 2. So you know that in total, there have to be 2 solutions. In terms of the real solutions, if you look at your x-axis, you would agree that there is no crossing. And again, because it's only degree 2, the graph is not allowed to turn back down. So how many x-intercepts do you see? None. So none of them are real, which means how many of them are imaginary? 2 of them. The total number of real plus imaginary always has to equal the total altogether. So in number 9, all 4 of them were real and none of them were imaginary. Where in number 10, none of them were real, which means they were all imaginary. Further, make sure that whatever you write for your imaginary has to be even, because remember, they have to come in pairs. So 0 is even and 2 is even. You can only have imaginaries in even sets. So how about number 11? So in number 11, again, it's supposed to be degree 4. That means that there is a total of 4 solutions. In terms of the real ones, If you go ahead and look at the x-axis, again, I think you would understand that there are no crossings, which means there are no reals, which means if there are 4 total, they all have to be imaginary. If you look at 4, 4 is even, so that's a good sign. Remember, it has to come in pairs. And then finally, finish up with number 12. So in number 12, because it's degree 5, we know there have to be a total of 5 roots. In terms of the real ones, we're going to count this as an M1, an M1, and an M1. Make sure that you would count any bouncing as an M2 and any flattenings, sorry about that, as an M3. So it looks like I have a total of 3 real graphable roots. Then looks like if I need 5 altogether, that means that there'd have to be 2 imaginary roots. Again, notice that 2 is even, which makes sense because they have to come in pairs. And if you're asking yourself, well, what on the graph tells me that there are imaginary roots? It actually is what's happening right here. The fact that the graph is turning and turning down and then turning back up and not actually crossing the x-axis, that is a clue that there are imaginary roots there. We're going to talk a little bit more about that later in the chapter, but this is a pretty good start. So thanks very much for tuning in, guys, and we will catch you next time.